Good morning, everyone. My name's Tim Faulkes. I'm the Director of Solutions Architecture at Aerospike. Today I want to talk about systems of record versus edge-based systems. Typically, Aerospike has been used for edge-based systems. Edge-based systems are characterized by having super fast-moving data. And obviously, Aerospike is renowned for having very, very fast data access. Edge-based systems have up to large sets of records. So we've got customers who have hundreds of terabytes of data. This is given to you at the speed of Aerospike. So typically we've got customers who have hundreds of terabytes of data with average response times in the millisecond timeframes, even sub-millisecond timeframes. But an edge-based system isn't typically the source of truth. The data in your edge-based system is useful for the specific use case that you've got there. So if I consider a customer profile, for instance, my edge-based system might have certain data that is necessary. So if I think of an advertising segment, I might have the set of segments that my user cares about recently, but it doesn't have historical data. It's not as big as the system of record sort of data. So system of records are smaller data. Typically the records are moderately small in the range of 1 to 2K. They can be bigger. Certainly we have people who are doing fraud detection in Aerospike. They use edge-based systems. They store transaction history in records, so they can be bigger. But typically we find they're a bit smaller than what is in a system of record. In terms of consistency, edge-based systems can typically either be strongly consistent or available. It depends on your use case. If I'm doing financial services, my edge-based systems had better be strongly consistent. If I get someone's account balance wrong, there's going to be hell to pay. If I'm doing ad tech and I'm not necessarily up to date or I've got the wrong data, it's not the end of the world. I've got ad tech customers who say to me, I've got a 50-node cluster. If I lose a node and lose a 50th of my data, I really don't care. They reload the data, it reforms, they do clicks, counts, and stuff like that. So it depends more on your use case as to what you need in terms of consistency. With a system of record, we tend to find that they are slower moving data. I don't need the data in milliseconds. Now, if I can get the data in milliseconds, it adds advantages. We had one of our customers who came to us. They were using a different NoSQL database as their system of record. It was an ad tech situation, and when they reloaded the customer, so imagine the TIM record isn't in the edge-based system. They haven't seen me for a period of time. I come and I start searching for something like batteries. Well, I'm not in the edge-based system, so they had to go and get it from the system of record. Now, that took minutes to get it out of the system of the record. Something like batteries, however, is a very short-term demand. Once I go and find my batteries, I buy them. I'm not going to search for batteries for the next period of time, be it months. So if it takes me minutes to warm up that data, I've lost those bidding opportunities in their case. So having the ability to get out of a system of record in the sort of millisecond timeframes that Aerospike is renowned for added significant value to them. But typically it can be slower moving data. It's data that you can have measured in seconds rather than milliseconds, but often milliseconds can be better. With a system of record, the data volumes tend to be larger. I might have terabytes, I might have petabytes. I have large amounts of data that form historical records as well as a complete picture of users or whatever I'm trying to look at. Systems of record must also be able to ingest and egest the data. I not only need to be able to take them in from the application, but I might be able to stream the data in from external sources, be it by Kafka or other mechanisms. I want to be able to have people notified when my data changes. So if they're doing analytics, they're running Hadoop clusters and they want the data in the system of record to be reflected into the slower analytics clusters, I want to make sure that when I can write into my system of record, I can replicate that into other systems. And as I mentioned, the system of record tends to be a complete picture. It is your source of truth. You can't lose the data. It has to be strongly consistent, and it contains your full view of whatever you're looking at, be it a customer, being an account, etc. It might be your transaction history. If I'm financial services, I'm doing fraud detection. Maybe my fraud detection only runs on the last years of history, but my system of record has to store the 7 years of history because of the audit and compliance. We typically find that edge-based systems and systems of records interoperate. There is data on the edge that has meaning to me for my use case. I want to be able to pull that information out of a system of record and effectively use the edge-based system as a cache. Now, I don't really like that terminology because it's more a geographical location I tend to find. So I might find that people have a TIM profile in US West because that's where I happen to spend most of my time. But if I fly to US East or I go to the UK or some other geographical location, they won't necessarily store my information there. So they'll try and suck that information from the system of record. And so you get this data movement going from the system of record to the edge-based systems. But also because the applications update the edge-based systems, the information from those edge-based systems has to flow back into the system of record. It is your source of truth. If you make changes to the record on the edge-based systems, you need to flow it back into that source of truth. If we're using a database as a system of record, there's several things we must make sure. We must make sure it's got full security. You can't have a system of record in many industries. If I'm looking at financial services and I don't have full encryption on rest, none of us want our companies to be on the front page of a newspaper saying, hey, we had a data breach. You have to do full encryption at rest. It has to be strongly compliant with standards. It has to be AS128 or 256. You want your data to be encrypted in flight. So going not only between your application and the database, but in the case of a distributed data store like Aerospike, it should be encrypted between the nodes and going between the different systems. So if we have two different Aerospike databases connected by XDR, it should be encrypted traffic going over there. And obviously you want authentication and authorization, possibly integrated with a centralized server which contains your security credentials like LDAP or potentially Kerberos coming up. So Aerospike supports all of this, and it makes it very interesting when you start using this as a system record. You have to make sure that you've got the right controls in place. You have to make sure that your data can't end up on the internet and yourself on the front page of the newspaper. Systems of record must have strong consistency. If this is your only copy of the data, this is your source of truth, and something happens and you have a network partition, you end up with two half clusters, and you start getting inconsistencies as a result of merging them back together, you've lost your system of record, you've lost your data. So in version 4 of Aerospike, we introduced the ability to do strong consistency. We guarantee that no acknowledged write can be lost. So this means you can trust it, you can store your data in there. There's a gold standard in the NoSQL database world called Jepson. It's run by a guy called Kyle Kingsbury. He prides himself on his independence. He's a rather acerbic character. He tested version 3 of Aerospike, and it was only an AP system. We only favored availability over consistency. We failed Jepson. You know? He could lose data. We knew he could lose data. When we introduced version 4, he retested Aerospike with strong consistency. And he could not break it. He could not find a way of breaking it. And so he gives us the quote of Aerospike does appear to provide linearizability through network partitions and process crashes. Not exactly a glowing recommendation. We sort of think he was a bit upset that he couldn't break our algorithm. But yes, you can go and read the full report online, but it is strongly consistent. He mentions a couple of things like clock skew, which are well documented, and we've got the version he tested was 3.99, and they have been fixed. Any holes he found have been fixed in subsequent versions so that if you do get clock skew, we say, no, you can't take writes. Your cluster doesn't necessarily agree on the clocks, and we can't guarantee the consistency. One of the nice things about Aerospike's strong consistency mode is when you do a write, you can't lose data. Okay, that's involatile. But when you do a read, you want a bit more flexibility. Do I want to be able to absolutely guarantee the latest data? So we have two main modes. The first is linearizability. I cannot tolerate a stale read in my application. We'll never give you a dirty read. We'll never give you a partial record. But if I'm reading a piece of data, I want to make sure that I absolutely have the latest piece of data, no matter what cluster splits and network partitions have happened. So if I'm presenting someone's account balance, you'd probably want linearizability. We have a slightly more relaxed mode called session consistency, which guarantees that if you wrote the data, you will absolutely read the latest data back. But if someone else didn't write the data, a different process, there's a very, very small chance in some edge cases that they might get an older version. These edge cases persist for milliseconds or seconds of time. It's only when you've got bad things happening with the network and data moving back and forth. Now, the session consistency is what most of our strong consistency customers use. The chance of getting a stale read is so low and there is a performance overhead of doing a linearizability. If I do a linearized read, I have to make sure that no one else in the cluster can possibly have another copy of the data that has a newer version. So when I'm doing a read, I not just go to one node, I have to go to several nodes to get that data. Session consistency is faster, and it's got strong enough consistency that we've got people doing interperson money transfers in Europe and they use session consistency. So they say, I'm happy for that risk. It's such a small chance getting a stale read, and I guarantee that it's not data that I wrote that I get a stale read of. I'm okay with that. There are other relaxed consistency read modes that I'll talk about in a moment when I talk about rack awareness. Strong consistency is minimal changes to your client. If you have an existing AP system and you want to turn it into a strong consistency system, from your client code, the changes are minimal. You have to specify, do I want to use linearizable reads or do I want to use session consistency? The nice thing about this is it's done on a per read basis, so you can choose. I've got some data that I really want linearizable, some data that I'm okay with session consistency, and I just need to specify. The default is session consistency. Aerospike divides your data into namespaces, I'm pretty sure most people know. The nice thing here is that you choose on a per namespace basis whether your data is strongly consistent or it's available. So if I'm something like a financial institution, I might have my account balance in a strongly consistent namespace. But what about fraud detection? Well, that tends to operate more on heuristics. It might make sense for some of those rules to live in an AP namespace so that you get some answer rather than no answer. Whether that's the case or not depends on the use case. Sir?
Question, how much difference between the availability versus strong consistency in latency?
Let me come to that on the next slide, please. I've got a slide on that on the next slide. All right. So then my last point, which the gentleman at the back just raised, it's high performance. Strong consistency, by default, if you look at the industry standard algorithms, incur latency. There's a performance penalty for doing strong consistency. Aerospike invented our own strong consistency algorithm, and I think that's why Carl was so disappointed that he couldn't break it, because it's like, no one can invent a new strong consistency algorithm. Well, we did it, and we went through and measured the performance. So you can see at the far column the availability mode. This is for this cluster that we had set up. We could do about 6 million transactions a second, read latency 220 microseconds, update latency 640 microseconds. If you use session consistency or sequential consistency, look at the middle column, you can see the numbers are almost identical. If you have replication factor 2, the performance penalty of moving from an AP namespace to a strongly consistent namespace is almost 0. As I mentioned, if you do linearizable consistency, there is a performance penalty. You have to, when you're reading, you're not just going to one node, you're going to multiple nodes, multiple network hops, so you do get a degradation in performance and an increase in latency.
About 100%, right?
It's,
twice slower.
it depends on, so it depends on your network, it depends on your replication factor, it depends on a number of factors. But there is a performance degradation, and we will work with you and look at your use case and say this is what we think, and typically we find that people benchmark it and find out the performance penalty of linearizability. But as I say, it's really rare for me to see a customer who uses linearizability. Almost everyone who uses strong consistency uses session consistency. It's good enough in the consistency that it's only really rare transactions need to have linearizability. So, if we're looking at some strong consistency use cases, we've touched on financial services. Obviously, financial services, almost always strong consistency. Maybe fraud detection, they're willing to sacrifice some consistency for availability. But then it comes down to, we've got one customer who does financial services. They run fraud detection on Aerospike. They use the AP mode. But the problem is, with AP mode, you don't know when you haven't given you the right answer. They don't care if it's not the right answer, but they'd like to know when it isn't the right answer. And AP mode, you can't tell, because we'll say, here's a piece of data. I don't know if it's right or not. Strong consistency, you'll know exactly whether the data is available or unavailable, because you get a special error code which says, I can see the data, but it's if I can't see the data because I've got a network split, you won't get a guess back. You'll get something coming back which says, you can't see this data. It's unavailable. We've traded availability for consistency. So anything obviously with financial services and monetary amounts must be in strong consistency. I was at an online company who has loyalty points on Friday, making pizzas of all things. And to them, their loyalty points are the same thing as currency. So in their case, even though it's just loyalty points, it had to be strongly consistent. They couldn't lose the data because it's effectively currency for them. It's not dollars and cents, but loyalty points matter. We find it strange use cases, social media. We've got a very large social media company who wants strong consistency, because if I go and friend someone and then I go and read the data and it split the cluster for some reason and it gives me that person isn't in my friend list, I think they've unfriended me, it causes social media rifts, all sorts of bad things happen. My son cares really much about this use case. It added so much to my coolness factor when I said they use Aerospike. All right, so Aerospike supports strong consistency. We also support a concept of rack awareness. Within Aerospike, we contain a federation of locally attached nodes. We like this. The latencies are predictable. When a write comes, it'll go to a node that's locally attached. You get great performance. But it doesn't offer you geographical redundancy. If I've got a system of record, what I typically want to do is have two closely attached geographical locations which have separate machines, and I want immediate consistency between them. For those of you who've got as much grey hair as me and you cast your mind back to the mainframe days, you know that you did a write into the mainframe and then you had set somewhere close by, sort of within a 10-mile radius, another mainframe which was taking those writes and replicating them synchronously. So you had the geographical redundancy. You lose a mainframe, you've got another one there which has a full copy of the data. Well, Aerospike has this concept of rack awareness, where we can say, I want you to have a cluster and I want you to spread that cluster across these two DCs. Now, typically these data centers are geographically close, so within that 10-mile radius, otherwise the speed of light becomes an issue and you get increased latency. If you do this, what we can do is we can set it up and we say, I want to have rack awareness. I want to tell Aerospike that each of these geographical locations is effectively a rack. Aerospike will then ensure that the master and the replica for a single piece of data exist on separate racks. So that means in my case of where I've got a split cluster, where I've got a stretch cluster, I will know that if the master exists on the left-hand side, the replica will exist on the right-hand side, and vice versa. So I have the ability to lose an entire rack or an entire geographical region, still have an entire copy of the data available in the other region, and continue with 100% availability. So I get full geographical redundancy. Yes, you incur some latency. When I do a write, I'm going to go to geographical location 1, perhaps, because that will be my master. It will replicate to geographical location 2, come back to geographical location 1, and then respond to me and say, yes, I've got that. So if they're on other sides of the country, you're going to incur significant latency. That's why we like them close together. I would typically also have a DR cluster. I'll have a separate cluster that's sitting there. XDR comes to it, so all the writes go to it, but it's there purely for recovery purposes. Now, this has some nice advantages, but also has some drawbacks. When I do a write, I have to spread the writes across the cluster. The strong consistency rules say that you must have written to replication factor number of nodes before it comes back. So in my case, replication factor 2, I must write to a master and a replica before it comes back. What about a read? Well, my application might be running in one of these locations. So let's say my application is running in location 2. When I do a read, half my masters will be in location 1 and half will be in location 2. So that means I'm going to incur time to go and read the data when it's across on location 1. But I've got a full copy in location 2. It's possible that data is fractionally stale. A write might have come in, it might have written to location 1, which is the master, and then it's in the process of replicating to location 2. But in some use cases, I can tolerate that. I can tolerate the stale reads if it gives me a performance penalty. So Aerospike can not only set it up so that it will guarantee you replicate the data across, but you can say, I want to prefer this region. So if my application is running location 2, it'll prefer location 2 and do all the reads from location 2. If I'm running location 1, I can prefer location 1 and it'll get all the reads in location 1. As I say, there's a very small chance of increased staleness in the reads. But think about if I'm running in a cloud providers. Say I'm running in AWS, for instance. I would set these up as two different AZs inside the cloud provider, inside a single region. I pay money for every read and write that crosses that location boundary between the AZs. My application is running in one location. I want to read from the same AZ. That means I will lower my costs and get better performance at a very small risk of having a slightly stale read. And many use cases can tolerate that increased risk of stale reads. So one of our social media providers did this, and they saved something ridiculous in terms of the inter-zone transfer costs. So the next thing to talk about is compression. Compression is done on a per record basis in Aerospike. So we mentioned that a system of record has large amounts of data. It can have up to petabytes of data. And if you're storing that data uncompressed, obviously you need a lot of storage to hold it. If you want to compress the data, Aerospike will support transparent compression. So the application doesn't know about it, it's done configuration driven, it's a dynamic parameter. You can choose to turn it on and off on the fly. Each record in Aerospike can be compressed individually, so I can say, I want that server to compress with Z standard, I want that server to compress with Snappian, that one's compress with zlib, for instance. It's very efficient. Changes are coming which will make it even more efficient, but the nice thing is that your data drops down to a fraction of the size it was. Now, the most common question I get when I talk about compression is, how much compression will I get? And the answer is, it depends on your use case. If you're storing the same data over and over, then you're going to get really good compression. If your data is random noise, you're going to get fairly bad compression. We've found customers who have in the range of 75 to about 60% compression. So it's good compression. So let's look at some hardware costs. Let's say I'm storing a petabyte of data. I've got a petabyte of business data. I've got 100 billion records, and each record is on average 10K in size. Work that out, it comes to about a petabyte of business data. Now, hardware costs these days are about $9 a gigabyte for DRAM, and in the vicinity of about 40 cents, 35 cents per gigabyte of storage. That's for a nice NVMe drive, and the costs have dropped dramatically on the storage in recent times. So if we look at this, you can see that I've got a graph which has broken down the storage numbers. So the red is DRAM, the blue is the storage cost, and then the grey is the total. So the left-hand side is, what would my cost look like for a system of record with a petabyte of data that was stored uncompressed? And with replication factor 2, it comes down to total cost is about $1.5 million. But if I can compress that, if I can take that amount of data and drop it down significantly, 60% compression, I drop down to about $700,000. With 75% compression, it's about $500,000. And so the costs drop dramatically. Now, these are rough estimates, so I haven't taken into account power, cooling, storage space, the actual servers themselves. So these are rough estimates, but it gives you some idea of the sort of cost savings you could get from using compression if you're using a system of record and you have large amounts of data. Let's talk about all-flash. One of the problems of storing trillions of records in Aerospike is every record requires a set of DRAM. It's got a primary index. That primary index is always 64 bytes, but if I've got a trillion records, or 100 billion records, and I've got 2 copies of them, well, let's say I've got a trillion records. 2 copies times 64 bytes, 128 bytes, so I've got 128 trillion bytes of RAM that I need. That comes out to 120 terabytes of DRAM. Okay? That's a lot. But system of records typically run slower. It's okay for me to take a few extra milliseconds to get my data. So what I can do is I can use all-flash to store the indexes. That 120 terabytes, I can move that out of DRAM and put it into memory. Put it onto storage. This works really well on systems of record. It also works really well on if I've got edge-based systems, and the edge-based systems have very small records. If my records are, say, 100 bytes, my primary index is 64 bytes, I'm approaching a 1-to-1 ratio between the amount of memory and the amount of disk. Particularly if I'm using things like AWS, which has very constrained ratios of memory to disks. It makes sense if my objects don't fit nicely into the patterns of those ratios that are enforced on me by the cloud providers, I can cut down on the cost by using all-flash at the cost of some increased latency. So Aerospike has these 3 storage modes. The first mode stores all the data in memory. It stores the indexes in memory, it stores the data in memory. It can optionally persist to rotational drive. Really, really fast, but expensive. Lots of memory is required. Our hybrid memory approach stores the primary indexes in DRAM, the information on the SSDs. And this works really nicely. About 80% of our use cases currently use this mode. But all-flash moves all that primary index memory into storage. So the storage contains not only the data, but it contains the primary index as well. There's a very small memory footprint for sprigs. A sprig is a small memory tree that tells us where the indexes live. I'll cover that in a little bit. But they're fairly cheap in memory. So if I look at some performance numbers, in-memory is obviously the fastest. There's almost no cost to it. It's getting the data out of memory. I have to do a network hop to the server, get the information and pull it back. So we typically find the latencies here are measured in the microseconds, the hundreds of microseconds. However, it's a very high cost of ownership. The amount of memory I need to get as my data expands, it expands dramatically. And so it's practical up to about a terabyte. If I want to use hybrid memory, then I can store lots of terabytes. I can store hundreds of terabytes. We've even got customers who are looking at storing a petabyte or more in hybrid memory approach. Latencies here are still really good. They're typically sub-milliseconds. If I'm using flash though, and I'm storing the indexes in flash and the data in flash, I can store terabytes and petabytes of data very happily with a very low cost of ownership. Yes, I pay for it a little bit in latency, but we're still talking 5 to 10 milliseconds perhaps. Most databases can't guarantee that for their hottest data. We're talking about this is your system of record, edge-based, not your edge-based data, but I'm willing to incur that extra latency cost. So what happens to my 100 billion records if I move to all flash? Well, I've taken this proportion that has fit into DRAM, that cost of the DRAM, and I've moved that out. So I ran through some actual numbers. You can see the numbers on the right there is all flash with 75% compression. Now you can see this, if you look really closely, the storage has increased minorly. And the obvious question is, where's the DRAM? Well, you can't really see it, but there's one line there which is the DRAM cost. The DRAM cost drops so dramatically that it's almost nothing. Each one of those sprigs costs about 13 bytes. So if I've got 100 billion records, it takes something like 5 gigabytes across my cluster of DRAM to store that information. So in this case, the total savings using compression and or flash for this hypothetical situation was about 77%. Don't quote me on this. You come to me and with your use case or my team and you say, this is what we want to do. We want to use compression, we want to use all flash. We'll measure your data and say, well, your compression ratio for your data in your use case is going to look like this. And then we can draw up these cost of ownership analyses for your use case. Okay, this is hypothetical. I cannot guarantee you'll get the same. All right. The other thing that makes a big difference is uniform balance. In Aerospike Legacy, the amount of data per server was about the same, but there was a skew. It was about up to 50% skew. So if I had a number of nodes, I couldn't guarantee the same amount of data on all the nodes. Under uniform balance, we will move the data so that it has almost exactly the same amount of data per node. This came from a customer. So this is an actual customer slide. They had non-uniform data here. They turned on for uniform balance here, and you can see the alignment of all the data. This their read and write, but the data did the same pattern. So imagine I've got nodes that are set up with 8 disks per node. I have this 50% skew that we see here. Well, that means that I go plus or minus 2 nodes on my plus or minus 2 disks on my 8 disks. That means I can't predict which nodes will have more disks than less disks. So each of my nodes has to have that 8 plus 2 or 10 disks per node. But I'm only really going to need 8. But some nodes would need 10. If you turn on prefer uniform balance, then you know that each node will have about the same amount of data, and you get into a situation where each would need about those 8 disks. So you get this cost savings of about 20% on the uniform balance, just turning on a simple flag, and it means that you get more parallelism across your devices. All right, so system of records have lots of data. What else could store this data? So when I was preparing this, I was trying to look at different ways we could store this data. Where could we store a petabyte of data? And I've got one customer who has very courageously come to me and said, we're going to go with an in-memory solution to store our system of record. Okay. They're talking petabyte of data. A petabyte is a large amount of data. You know, if you stored that on DVDs, which hold 4.7 gigabytes, and you stack them end to end, it'd be higher than the Empire State Building. Okay, it's a lot of data. So let's look at it. I'm storing a petabyte of data. I want to look at an in-memory solution, Cassandra and Aerospike. Now, I'm going to cheat. I'm going to cheat a few times in this. I'm going to pretend Cassandra has a strong consistency mode and in-memory solutions have strong consistency. If you read Jepson reports on the appropriate things, you'll find that they don't, that they have ways of losing data. But let's ignore that. Okay? So let's look at the petabyte of data in memory. I tried to slice and dice this in the most optimistic way. I tried to see what happens if we use commodity servers, what happens if we use really RAM-heavy servers, what happens if we use DRAM and PMEM. And I tried to look at the best prices I could find on the internet for these things. So these numbers aren't just made up. These numbers are actually do some research on the internet and see what price I can get. Well, commodity servers came out to $42 million. The heavy DRAM came to about $32 million, but it's over 3,000 nodes. DRAM plus PMEM. PMEM hasn't been officially released, so I can't get pricing. It's meant to be cheaper than DRAM. But you're still going to be talking about many millions of dollars just for the hardware for this. So I wrote this mode off. Let's look at Cassandra. Okay, Cassandra's a really good database. I really like it. It's got a great architecture. It scales really well. We have there are people around the globe who have thousands of nodes of it. We do, however, find that we do a lot of replacement of Cassandra. People look at Cassandra and there's maintenance issues, large clusters. You need a small army of people who will maintain the clusters. And we find that we do a fair number of these replacements of Cassandra. So on the DataStax website, DataStax, for those who don't know, is the people who effectively sell Cassandra. They have a planning guide, and they say the recommended maximum amount of data per node is a terabyte. And if you go over terabyte, here's this list of horrible things that will happen to your cluster. It'll take a long time to add a node, it'll take blah, 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 blah. So I said, all right, well, we'll do a terabyte of data. They're quorum-based, so they need 3 petabytes of unique data. Okay. That's going to be 1,000 nodes. 3,000 nodes. Their tables have fragmentation problem. It's the same way Aerospike has fragmentation, so you've got to consider that when you're doing your capacity planning. So they need about 6 petabytes of data. Now, the total storage cost, you can see I've broken down the cost. They need about $6 million for their hardware cost. One thing that's interesting, though, is when people come and talk to us about performance, they talk about the average performance. Now, average performance doesn't really mean much to most people. You care about the effect on your customers of what happens with the slowest latency, your P95 or your P99. As you add the number of transactions to the database, the probability of hitting something which is a P95 or P99 increases dramatically. So you can see mathematically I've worked it out. If I'm doing 250 business transactions, probability of hitting a 95th percentile transaction is 99.99%. Pretty much guaranteed. Probability of hitting a 99th percentile is 91%. So if your average is great, your average latency is great, but your 95th percentile or your 99th percentile is measured in seconds or something like that, and you expect your system of record to be able to deliver in millisecond timeframes, you simply can't do it if you've got a large number of transactions per business transaction. And this is a graph came from one of our customers. They were using another system. They had this sort of number of transactions, high number of transactions per business transaction. And you can see when they switched over to Aerospike, they moved from hitting their latency numbers 98.5% of the time up to their worst case was 99.95% of the time. So it makes a difference. If you need this latency, even on a system of record, you still need to consider the number of business transactions. All right, so we looked at Cassandra. Let's look at Aerospike. Now, Aerospike sacrifices the amount of memory by putting them onto storage. We optimize for SSDs and flash storage. They're much faster than they used to be. NVMEs are really fast. They're not as fast as memory, but they're still pretty good. But it's all hot. Aerospike stores the information. It doesn't have this concept of data lives in memory, data lives on disk. It's all the same sort of speed. So given this, I looked at, okay, we've got 4 petabytes. We're not quorum-based, so we only need 2 copies of the data. We need to store 4 petabytes of data. It's easy for me to get 6.4 terabyte drives. I've got customers who quite happily have 10 or more SSDs per node. So let's put 10 of these in so I can get 64 terabytes of data per node on SSD. My 4 petabytes comes down to 63 nodes. I don't need thousands of nodes. I don't need an army of workers to maintain this. I don't need to have committers to an open source repository to be able to maintain this. And you can see the total hardware cost dropped fairly dramatically, down to about $1.5 million for this. Note this is without, sorry. Yep. So yes, I then graphed this. I made some assumptions, okay? Cassandra does its compression on a column basis. It's a column data store. Now, typically the data store in a column is more consistent than the data store in a row. So I assumed that the Cassandra compression is 75%. I assumed the Aerospike compression is only 60%. I assumed the Cassandra servers were $2,000 each. That's pretty optimistic when you look at the prices. I assumed the Aerospike servers are $25,000 each. We've got 10 NVMe SSDs in. They're going to be more expensive. But when you look at the total cost of ownership and you look at the number of nodes, when you consider the people you need to run a system of record, how many people does it take to maintain 63 nodes? How many people does it take to maintain 3,000 nodes? The cost savings of storing large amounts of data in Aerospike, the system of records, the total cost of ownership is enormously in Aerospike's favor. And we find that we do a number of replacements of things like Cassandra, not based on technical merit, not necessarily based on the speed, but simply on the cost of ownership. And then they get all the other advantages of Aerospike over other databases for free. All right, just one other quick thing I want to mention. I'm pretty much out of time. We're storing 64 terabytes a node in Aerospike. That's a lot of data. What happens if one of those nodes goes down? Well, we've got to start migrating data. What if we have to cold start a node? I need to reboot my node because the operating system, I patched the operating system and I can't just do a warm restart from Aerospike. I need to reboot. Okay, well, that's an issue. Aerospike now supports PMEM, the Intel Optane PMEM, and it's done in persistent mode. This is typically done for indexes. So when you have these large nodes, you want to store your indexes in PMEM so that if you do have to do a cold start, the time taken drops dramatically. If you don't use PMEM, your information is stored in memory. Rebooting the node, it's got to scan all your drives. It's got to read through 64 terabytes of data to work out where the information is and rebuild its primary index. If you store the information in PMEM, then it doesn't need to do that. It knows its index is consistent, so even doing an operating system restart means that when you come back, you've got all your indexes there, and the time taken drops by orders of magnitudes to do these fast restarts. And then some other caveats that I need to mention. The numbers here, as I said, are hypothetical. They do not apply to your use case. Please don't take these numbers and say, well, Tim guaranteed that we're getting 75% reduction in blah, 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 blah. I would deny all culpability here. But we will work with you if you come to us and say, this is what we're trying to do. We'll work with you and get the numbers that are applicable for your use case and to do these cost of ownership analyses for your particular use case. Some of these features do require additional licensing. So if I look at All Flash, it could require compression at rest. They require additional licensing. But the cost you save, the cost of the licensing should be far outweighed by what you save in the hardware when you're trying to build up these clusters. And the larger the scale, the more you save. All right, any questions?
Just a question about PMEM.
Yeah.
Is it the same performance as DRAM?
Not exactly. Sorry. Great point. So the question was, does PMEM have the same performance as DRAM? It's not exactly the same performance, but it's much faster than reading off SSD. But it's not quite as fast, but it's a very small difference. I don't know exactly the difference, but I think it's in measured, so let's say 10%. I've seen a graph of what it looks like. But yeah, it's really fast, and you can get bigger DIMMs. So you can get up to 6 terabytes per node quite happily on PMEM. Any other questions? All right, thank you kindly. I appreciate your time, and please remember that the sessions have feedback, so if you want to leave feedback, go into your app on the Aerospike.com Summit, find the session and give whatever feedback and say if it's the right sort of level, too deep, too complex, or whatever. Thank you kindly.